Okay, so when I was giving a talk at MPI, I was informed by my boss that simple is a very overabused word, so I might want to remove it, but we can discuss it at the end. Okay, so as you all probably know, the compression is becoming increasingly popular nowadays, and there are several compression standards, and many of them have some stringological feel to them, but today I'm going to talk about grammar-based compression, which means that your word is going to be represented just as a context-free grammar which generates exactly one word, which is called straight-type program, or SLP, for some historical reasons that I do not really understand. And this is perhaps not the most practical grammar compression model, but it has several advantages. For instance, it's very short. I didn't draw any picture, and you still probably understood what I meant. It's good for later preprocessing, so this natural inductive definition of a grammar makes it easy to make some algorithms which work on this compressed representation without the decompression. And and it has some relation to block compression, which makes it useful, at least in some applications. Okay, so imagine that you would like to use your grammar compression. So in order to do that, the first thing that you would like to have is that you are given the word and you would like to output the grammar, probably the smallest grammar that you can make. But this turns out that the bad news is that this problem is already NP-complete. The decision version of this problem is NP-complete, which is not that good, but fortunately there are several approximation algorithms. Well, there are actually several of them which have the currently best approximation ratio, which is logarithm of n over g, when n is the size of the input word and this g is the size of the smallest grammar. I will just say that it's logarithmic. This division by g is nice, but it's not that important in most cases. And today I will give yet another algorithm for this problem. And I will try, probably someone will ask me whether it's really so simple, but still I would like to claim that it is. But I have to be honest that all the previous ones are okay. I mean, they are not bad and they have many advantages on their own, but my main claim would be that if you would like to explain it to your student, then this one is probably simpler than the other ones, like you use less Blackboard. Okay, so I've told you that there is some relation with to the block compression, so probably all of you know what's LZ77, but since this is broadcasted, so also for the people who actually watch it, then LZ77 is a compression standard which represents the word as a concatenation of some fragments. Okay, so if you have a word, W, and it's represented as a concatenations of F1, F2, F3, and so on, and each of those fragments can be either a single letter, which I will call free letter so that it's distinguished from other letters so that it's clear, or it can be a factor, which means that this is some part which already appeared somewhere before. Those parts can overlap, so we can say that this something occurred here and they overlap, that's okay. So for instance, and the size of such a factorization is just the number of factors that you are using. Okay, so whether this is just a single letter or a very long block, then we treat it as size 1. So for instance, for this word, this is actually the smallest factorization. So whether this A is a factor or a free letter, that doesn't matter because this is size 1 anyway. But for instance, this part was already here. So this is one factor. This is also one factor which appeared here. And you can see that the size of this factorization is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the size of the factorization is 11. On this particular factorization, and this is actually the smallest factorization, if I didn't make any mistake. And the good thing about LZ77 is that for first thing, you can calculate the smallest factorization in linear time, assuming some computational model, but let's say it's in linear time, and that the smallest grammar is not smaller than the LZ77 factorization. Because basically a grammar is this sort of representation, but perhaps satisfying some additional conditions. Okay, so since it's computable and it's smaller, then this is a natural lower bound for any algorithm which would like to output the grammar, the smallest grammar. Okay, so imagine that we would like to have a grammar. We have a grammar for some word, and you can I didn't write any labels and names and non-terminals because this is not that important here. But what I would like to say is that you can think of a grammar as an iterated pairing. Okay, so you are given a word, you pair some of those letters. We are so lucky that none of the letters is left out. So you pair of those letters, and for each pair you create a new symbol, a new non-terminal of the grammar. And when those pairs are identical, then of course those new symbols are also identical. Okay, then you forget the original letters, and now you pair those new symbols, and again, any of them are identical, then they are called the same, and you do it until you get just one symbol. Okay, so the whole grammar is in fact can be seen as iterated pairing. You get something, you pair, you identify the copies, you replace, and you iterate this process. And in the end, the size of the created grammar up to factor 2 multiply 2, I shouldn't use word factors, up to multiply of 2 is just the number of different pairs that you have seen during your computation. Okay, so imagine you are getting a word. So what's the most natural pairing that you can think of? You just take the word and first and the second, third and the fourth, fifth and the sixth and so on, and just the last letter is left on its own. Okay? So then if you were to iterate it, then in the first round you get n over 2 non-terminals, in the second n over 4 and so on, so you get a linear size grammar, which is not that great. So we would like to have some better bound. For instance, if we knew that this part and this part are identical for some reasons, for instance, they are generated by the same non-terminal in the optimal grammar, then we would like to say that also the pairing is identical. But we do not even know how the grammar looks like, so we cannot hope for that, and we cannot use this knowledge in any way, at least seemingly. So let's think about this LZ77 factorization, which we can calculate in advance. Okay, so if this were a LZ77 factorization and this is a factor, then it also occurs somewhere before, so the factorization should be the same, because and the pairing should be the same, because afterward this is exactly the same word. But it's not, and the only reason is because there's some space between them and the parity is different and they are paired differently, okay? And this is clearly wrong, so we fix it. Yeah, so we pair this factor exactly the same as it was paired in its definition. And to do that, we just need to make some slight changes at the beginning and the end. Okay, but it's still paired differently because this one symbol is not paired and this is paired with its neighbor, but this neighbor is probably different. Okay, so we just shorten the factor because we cannot do anything with that. And now everything is fine, so the factor is paired exactly the same as its definition. Okay, so, and this will be basically our algorithm. So we will create a pairing, and the pairing is exactly the same as grammar. We will just iterate it, and the pairing will have 3 properties. The first property, sorry, I forgot to tell you. In the last round, there were 2. Here there are 2 unpaired letters, so we just pair them. There's no reason why we shouldn't pair the letters if they are next to each other. We spoiled something, so we fix it at the end. Okay, so there are 3 properties, and the order is important, so I'll read. There are no consecutive unpaired letters, and that's quite clear. If they are unpaired, then we just pair them. The factor is paired exactly the same as its definition, and this is also should be clear, because this is the reason why we are using actually the LZ77 factorization, to pair everything in the same way. And the third condition is a bit technical, so we would like to say that the first 2 letters and the last 2 letters of the factors are paired. Because without this condition, those 2 previous ones get a bit ambiguous. If the pairing goes out, or if there are some odd, if nothing is paired or the length is 1, then you do not really know what should happen. So this third condition makes sure that everything is well defined. Okay, then that's a technical thing which makes everything easy, although we could do without it. And the important consequence of such a pairing is that in some sense, we can inherit the factorization. So if we have a factorization, we have the pairing. The only reason why we have this pairing is because we want to replace pairs of letters by a single letter. Then the factor is well defined also after those replacements. So we have the pairs here. When we replace pairs of letters with single ones, then the factor is still defined as its definition. The offset is different, so we need to use some pointers, but otherwise we can inherit the whole factorization. and the number of factors is the same. The number of free letters changes because some of them are compressed into one, but the number of factors is the same. Okay, so how would the algorithm look like? So we scan the word from the left to the right, and as long as the text has at least one letter, which means that we still should produce some pairing, we scan the word from the left to the right, and if the letter that we see is the first letter of some factor, then we check if the factor is non-trivial, in the sense that it has more than one letter. If it has exactly one letter, then we just demote it into a free letter, because this is not really a factor. We cannot pair anything without this factor, so we replace it with a free letter. Then we look, if this is not the case, then we check whether we can copy the pairing, so whether this first letter of the definition is paired, is the first in the pair. So in this case, this is wrong because it's paired to the left. So we shorten, in such a case, we shorten the factor by this one letter. Okay, and in this proper case, when everything is fine, so this is copied here, then we simply copy the whole pairing. Okay, so we have the pairing for the factor exactly the same as for definition, and we just slide the whole window till the end of the factor. But now there can be some problems at the end, because this should be also paired, but with something inside. Okay, so and this is not the case, so we remove those letters which are. So at the end we cut the letters until we find something which is the last letter of the factor. And since the pairing here was already satisfying all our technical conditions, this means that in the worst case we cut two letters. Because it could be the first letter in the pair, so we cut it, then it could be an unpaired letter, we cut it, and then that's the second in the pair. And the same applies also at the beginning. So in the worst case, we cut two from the beginning and two from the end. Okay? And if this letter, the other case is that this letter is a free letter, which could be also a free letter which we just popped from the factor. Okay? So if we pop it from the factor, then we also run this part. And if it's a free letter, then we check whether the previous one is unpaired. And if it's unpaired, then we pair them, because there's no other way what we can do. Okay, and that's all. And you can easily check that the invariants are preserved. There's one case which I omitted, and I lied a little bit, but it's technical, but fixable. Okay, one case is missing, but I wouldn't like to explain it in too much details. Okay, so the only reason why we do the pairing is to actually replace the pairs by new letters, so we do it. So letters inside pairs within factors are just replaced. Pairs of free letters are replaced by a new free letter, and if the letter is unpaired, then it's left as it was. If it was inside factor, then it's still inside factor. If it was a free letter, then it's still a free letter. Okay, and we can inherit the factorization. So this was a factor, and this was its definition, and now this is still a factor which has exactly the same definition. Okay, the offsets change a bit, but we can use pointers or something else to actually still keep to know the place in which this definition is. And and the free letters, well, there are two cases. This is the free letter which was just preserved, and this is the free letter which was obtained from two old free letters. Okay, so the only thing, and it should be quite clear that you can make one such round in linear time if you do it properly. Okay, so the only thing that's left to say is the analysis. So the number of different pairs that we actually consider. Okay, so the number of non-terminals that we create during the pairing, during the whole algorithm, is just the number of different pairs that we make during the pairing. Okay, so if we are inside the factor, then we cannot make any new pair, because everything that's here was already here. So if we consider the almost always the leftmost pair, then within the factor we cannot make a new pair. Okay, so every pair that's inside the factor by definition also occurs somewhere to the left in its definition. Okay, so the only moment in which we can create a new pair is when both of those letters are free. But if both of those letters are free, then it means that when we replace it with one letter, then we lose one free letter. So for every non-terminal of the grammar that we create, we lose one free letter in our factorization. So we just need to calculate the number of free letters that we create, and this is exactly the upper bound on the number of non-terminals of the grammar. Okay, so I've already told you that when we have a factor, then we can cut at most 2 letters from the left and 2 letters from the right. Okay, because we cut the letters if those are not the first or the from the beginning we cut if this is not the first in the pair, and from the end we cut if they are not the last in the pair. And there are no 2 consecutive unpaired letters. So 2 from the left, 2 from the right. And since everything, there are no 2 consecutive unpaired letters, which means that everything shortens by a constant fraction in each round. So when you look at a fixed factor, it will shorten by a constant fraction in each round, so it will terminate after logarithmic number of rounds, and in each round it will introduce a constant number of letters. So in total we will introduce some overall factors, logarithm over those sorry, times the sums of the factor, times of the factors, and we know that all factors sum up to the length of the initial word, so this is minimized when all those factors are equal, n of length n over L, which gives this upper bound, and since L is at most G, then this gives also this upper bound. Okay, and that's it. Okay, so the question that remains is how good is this approximation ratio, taking into the account that at the moment the best lower bound is still constant, but it's achieved for very single strings. Okay, so it might be that still the lower bound is much higher, but on the other hand, we do not know. So maybe the approximation ratio should be lowered, and maybe for some simple classes of strings, actually the approximation can be better for those algorithms, or maybe for some others. Yeah. Okay, thank you.
So thank you. Are there questions?
So 2 things. First of all, do you know if it works in practice? I mean, I assume it works. Do you know if it works well in practice?
No, no implementation, if that's the question.
Okay. It sounds simple enough that somebody could do. Second thing, you said yesterday on the walk that it's not balanced, but it seems that the SLP has logarithmic height. So it's just the subtrees are not, like,
yes,
it's not weight balanced or something like.
The total depth is at most log n over G, but perhaps some subtrees are very...
Okay. Do you think you could make it height or weight balanced?
I don't know. I have some doubts.
So more questions?
I implemented once the method of Wojciech-Ritter for converting LZ to grammar, and the approximation bound was in practice something like 4. But then that was bad enough compared to repair, for example, which has very bad worst case approximation ratio. So my question is, do you think it is possible to design some method like this that has a good worst case bound, but is never worse than repair or some other method that works well in practice?
Would be nice, but I don't know. So I have I don't know. So I understand that it would be nice, for instance, to just make a small twitch to repair so that it would have a guarantee, but I do not know how to do it.
But wasn't your compression by recompression, it was a lot like
this
repair.
Was much more than just a small twitch.
Okay.
So more questions? I have one small question. So you start with a word. So if you start with SLP or LZ factorization, can you process it in linear time in the
I don't know,
site?
but I doubt it. So with SLP, maybe. With LZ77, I don't think so.
Okay, so thanks for the talk.